Ever wondered how much safer your work at height operations could be? Imagine a world where every potential hazard is detected before it becomes a problem. Meet Tracker AI's smart PTZ camera system. This isn't just any camera, it's a game changer in work at height safety. Safety is paramount, right? It's the foundation of a productive and happy workforce. Despite stringent regulations, accidents still happen. Traditional methods often fall short in preventing these incidents. Enter Tracker AI's smart PTZ. This advanced system is designed to fill the gaps left by outdated safety measures. Tracker smart PTZ cameras deliver unmatched oversight so you can spot hazards before they become accidents. Offering 24/7 monitoring, it detects work at height safety hazards instantly, no matter the time of day or night. Think about it. Real-time monitoring, automated alerts and even fall detection. It's like having a safety manager who never blinks. Real-time alerts trigger immediate action, ensuring that potential dangers are addressed before they escalate. Automated surveillance significantly reduces human error, making your work site safer and more efficient. It even detects PPE and welding work compliance, ensuring that all workers are properly equipped. Ensure every worker goes home safe. That's the ultimate goal, isn't it? Ready to elevate safety? Stay safe, stay smart. With Tracker AI, you're not just upgrading your equipment, you're upgrading your entire safety culture. The Tracker Smart PTZ camera features advanced AI algorithms that are constantly learning and adapting to new safety challenges. With 360-degree rotation and high-definition video, it covers every angle, leaving no blind spots. You can decide which areas to cover, what to detect in each area through a simple online procedure without ever leaving your seat. Through the setup, you can monitor what is happening on the ground in real time remotely. In a recent case study, a manufacturing plant reduced accidents by 40% after implementing our system. Features include night vision, advanced monitoring for PPEs, work at height and welding activities, including real-time analytics, making it a comprehensive safety solution. Our team of experts ensures the highest quality and reliability, constantly innovating to meet your safety needs. Plus, our dedicated support team is here to assist you 24/7, ensuring that you get the most out of your investment. Join the revolution in safety with Tracker AI's smart PTZ camera system. It's time to take your safety measures to the next level. Visit tracker.live to learn more and get started today. Together, we can create a safer, smarter future for everyone.
Welcome to another episode of Hakla Podcast, where we explore the systems, strategies, and innovations that keep people, projects, and planet safe. In this episode, we are joined by Mr. Urvesh Vala, a global expert in materials, corrosion, and integrity engineering, with over 25 years of experience working across green hydrogen, LNG cryogenics, offshore platforms, refineries, and nuclear systems. Mr. Urvesh has led safety critical engineering on projects for clients like Shell, ADNOC, Aramco, ExxonMobil, and Total, and many others. His expertise spans hydrogen embrittlement, failure prevention, NDE, corrosion control, digital integrity management, and much more. Today, we are talking about how safety is designed into the very materials and systems powering the energy transition, and what it takes to build reliable, risk-resilient infrastructure from the inside out. Thank you, sir, for joining us today. I would request you to please introduce yourself for our audience.
Thank you. Thank you for giving me this opportunity. You already briefed about me, but I just add a few things related to my professional accomplishment during my 25 years of services. That is, I'm a part of AMPP, which is NACE SSPC joint venture, professional organizations started in US, and other is like I'm part of ICOR, which is in
Mm-hmm.
UK.
Okay.
Also, I'm part of CII, CMD, that is Corrosion Management Division of Indian professional body.
Okay.
Also, I have experience with other professional bodies like Indian Institute of Metals, Indian
Mm-hmm.
Institute of Welding,
Okay.
Indian Institute of Non-Destructive Testing, and
Mm-hmm.
I'm a part of IITs
Mm-hmm.
for their syllabus improvement
Okay.
suggestions,
Mm-hmm.
and also collaborated with uh, state colleges for
Mm-hmm.
their BOS, that is Board of Studies
Okay.
associations within
Mm-hmm.
India.
Okay,
And
sir.
with that, I have written almost around 150 papers, research papers
Okay.
in
Mm-hmm.
international and national conferences, and
Mm-hmm.
I get recognitions across globe as
Mm-hmm.
a corrosion specialist.
Okay, sir.
Thank you.
Thank you, sir, for joining us today. I'm really happy to have you today on my show. So let's get started. So, safety is often defined in design. How do material selection decision impact long-term safety in hydrogen and cryogenic systems?
Yeah, it's a very interesting question, and is this question is demand of the day, as such, because you know that Indian market or Indian companies are going forward for hydrogen blending
Mm-hmm.
in the pipeline business. So they are keep adding percentage of hydrogen, and now they are increasing.
Okay.
So yes, of course, safety and material selection is a challenge for hydrogen especially, and cryogenic, of course, is having its own way of handling with respect to safety and material selections. So
Mm-hmm.
just to say that safety in hydrogen and cryogenic systems, that is largely decided based
Mm-hmm.
on the material of constructions, which is the initial stage of any engineering to start.
Mm-hmm.
And then beyond that, the welding, fabrication challenges, and even uh, the operators' qualifications play important roles. Of course,
Okay.
fabrications having their own challenges with respect to code standards, boundaries. So those
Mm-hmm.
things are to be managed with respect to time.
Okay.
So normally, when we see the failure, which is in case of hydrogen or in case of cryogenic
Mm-hmm.
vessels or piping, is catastrophic in nature. So it
Okay.
happens suddenly. So is not like it's uh, taking your alarm something before it happened. So
Okay.
this is why this particular material is to be handled very carefully.
I see.
Normally, this material, which we think of for hydrogen and oxygen or cryogenic services, normally cryogenic services are used for oxygen, nitrogen, which is at
Mm-hmm.
its liquidified stage. So
Okay.
they condense and they put into the liquid stage so
Mm-hmm.
that the carrying of those gases in the form of liquid is easy.
Mm-hmm.
As you are aware that when it is converted into liquid, it reduces to thousands times than the gas phase because of the
Mm-hmm.
liquid molecules are very closely attached together than gas. So
Right.
in this case, if you see the material selections challenges with respect to safety decisions in hydrogen
Mm-hmm.
and cryogenic system, the
Mm-hmm.
main parameters which is important is the extreme temperature which this services are having, extreme
Mm-hmm.
pressure cycles, upset scenario, and unique degradations mechanisms because of the strength-based material selections is
Mm-hmm.
in the requirement. Normally,
Okay.
strength is not the criteria for the increasing hardness. It is
Mm-hmm.
normally considered for its toughness requirement if it is a cryogenic material, or if
Mm-hmm.
it is a fracture resistance in terms of its life cycle assessment. So both hydrogen and cryogenic equipments are normally having such mechanical properties which is
Okay.
important beyond the normal merits.
Mm-hmm.
Also, if you see that the bigger challenge is to have low strength carbon steel for such material to be handled.
Mm-hmm.
Also, there is careful control of microstructures and hydrogen uh, as a gas. You know the hydrogen is the thinnest gas out of all the gas. So that handling hydrogen within the vessel is a challenge. So
Mm-hmm.
we have various standards which is normally used for hydrogen system like ASME B 31.12, or you can use ISO 1114. So
Okay.
4 times 1 4. They are generally used for designing this hydrogen and cryogenic service requirements. So
Mm-hmm.
cryogenic services are normally used based on ASME boiler and pressure vessel section 8. Also, it's gone by European standard called EN 13445. So
Okay.
these particular standards are normally used with different combinations metallurgy. For
Mm-hmm.
example, if you say cryogenic system, then austenitic stainless steel is the most common material normally used. Other
Mm-hmm.
than this is aluminum alloy or nickel-based alloy, because nickel give you high temperature strength,
Mm-hmm.
even at
Okay.
cryogenic temperature. So
Okay.
these are the normal codes and standards which we can go forward. And now biggest challenges is for the LNG
Mm-hmm.
pipings and terminals which we are thinking of. So that is normally operated with the help of ASME code. But here
Mm-hmm.
challenges are important is in terms of MDMT, that is minimum metal design temperature. So this give you quite interesting characteristic with respect to CHARPy impact testing requirements. So these are the things which is for us to address with respect to hydrogen and cryogenic equipments.
Okay, sir. So, sir, what are the major risks related to hydrogen embrittlement, and how are you addressing these in pipelines and storage applications?
This is also a very interesting questions because hydrogen embrittlement is very uncommon phenomena which normally not discussed in detail, because if you see traditionally 8 forms of
Mm-hmm.
corrosions is not categorized into this hydrogen embrittlement damage mechanisms. So if you
Mm-hmm.
go with the help of API 571, which is a standard which says
Mm-hmm.
many damage mechanisms, and out of this, hydrogen embrittlement is the damage which is very silent in nature. Is not occur
Okay.
uh, uh, progressively. So it is very silent, but at the same
Mm-hmm.
time, when you see uh, the corrosion behavior of this particular hydrogen damage mechanisms, embrittlement in terms of the impurities which the plate material is having. So normally hydrogen embrittlement is one of the most misleading damage mechanisms in engineering. It often
Mm-hmm.
shows no visible warning until it ruptures. So you will to
Okay.
say that this is a catastrophic failure in its
Mm-hmm.
own design. So there is a loss of with respect to the constructions and other parameters, because it's a sudden failure and chances of fatality or safety hazards are much higher in terms of this. So to understand this damage mechanisms, there are certain uh, approaches which is normally there with respect to material control. So that
Mm-hmm.
is limited to hardness. So whenever you have a hydrogen embrittlement, that is a requirement of hardness control. Avoid high strength steel selections. It requires a
Mm-hmm.
soft material. Also,
Okay.
you have to go for specifying tight chemical compositions limit. So by
Mm-hmm.
doing so, you can control with respect to material. Similar challenges is for welding also. That controlled welding procedures is also important. Hydrogen controlled consumables are required, which is available in
Mm-hmm.
market with many suppliers. Post weld heat
Mm-hmm.
treatment is again an important parameter for this mechanisms to control.
Mm-hmm.
Also, it is going to have a strict hardness acceptance criteria. So these are the controls related to welding and heat treatments. Stress
Mhm.
management is also a challenge because you have a smooth geometry of equipment and piping. There is no stress riser points available, or you have to
Mhm.
avoid stress concentrations when you do fabrication of such equipments and piping.
Okay.
This is also in line with environmental control, like managing impurities, moisture, and
Mhm.
operating envelopes to reduce hydrogen pickup. So these things is really challenging for minimizing hydrogen embrittlement. Then the question is like from where we can understand this. So there are many international standards which are supporting, or you can refer like NACE MR0175 or nowadays
Okay.
ISO 15156 that limits the
Mhm.
hardness and material chemistry to prevent hydrogen assisted cracking. So you can refer this standard. Also, if you
Okay.
want to go for piping, then you can refer ASME B 31.12, which introduce
Mhm.
hydrogen specific design factors and material
Mhm.
performance envelopes. So that is also possible. And if you want to understand in depth, so there is a API standard which is available in European standard, API
Mhm.
RP 941, which is giving you informations based on Nelson curve, which normally used to design metallurgy based on hydrogen effect. So
Okay.
these are the things, and if you the last things which you are asking is related to pipeline and storage
Mhm.
mitigations factors. That is normally as listed uh, in the discussions that a restricted hardness in weld and heat affected zone is the primus requirement. Also avoid high strength steel uh, using certain mechanisms by which fracture mechanics is to be understood very correctly. If your
Mhm.
high strength steel is used, then you have to use the phenomena called fracture mechanics into considerations of this particular damages. Also,
Okay.
applying strict welding procedures, qualifying hydrogen control consumables, and
Mhm.
designing of lower stress utilizations areas with respect to the design
Right.
uh,
Right.
in case of cyclic service requirements. Normally there is many services are there, but when you are specifically designed for this problem, then you have to go for such control. So
Mhm.
in nutshell, the hydrogen does not break a system quickly. It wait
Mhm.
patiently for stress defects and time to align to get the
Okay.
failure.
Right. So, sir, it's kind of a unknown if we do not follow the right procedures for safety because the explosion is like it's an explosive thing. It's not a small fire or something. The damage will be extreme.
Yeah.
Okay.
Yeah,
Okay.
correct. The other part, like what you say correctly, like hydrogen, when it get failure, it's get fire very easily. So any equipment is get affected because of the leak of hydrogen. It's always
Mm-hmm.
you can see with the fire.
Okay. So I am assuming there will be an explosion.
Yes,
Okay. It is dangerous.
yes, of course. So many precautions are there, and normally when you see such constructions, they avoid flange joint constructions. They normally use weld joints. So
Okay.
that will because any mechanical joint is of leak. So
Mm-hmm.
if high pressure hydrogen service are normally they avoid using uh, flange joint.
Okay. So, sir, moving forward, cryogenic systems operate under extreme pressure and temperature. What failure scenarios do you design around to ensure safety?
So, cryogenic systems fails in uh, gradient and it's also hydrogen. Normally,
Hmm.
for cryogenic, major damage mechanism is a brittle fracture. That is
Okay.
because of thermal shock or a rapid variations. that can
Mhm.
lead to such failure. That's why design code focus on heavily on what is like toughness. Toughness is the property which is very governing properties for designing cryogenic equipments.
Mhm.
So I that crash system damage design against rapid catastrophic failure model that we governs with the standard called Section 8 Division 1 and 2 ISO 120 NFP 59A. Normally it is used for LNG systems. And
Mhm.
normally this design address the risk of selecting material with verifying fracture toughness at minimum design temperature, managing thermal gradients during cool down or warm up to prevent cracking. So that is another cracking damage mechanism which is there associated to cryogenic equipment. Also designing for pressure relief during phase changes. So
Mhm.
these are the things which is important to manage brittle fracture risk in present scenario.
Okay. Thank you, sir, with by sharing your insights. I mean, that's really helpful. So let's moving on. Non-destructive testing plays a key role in detecting flaws before they become failures. Which technique do you trust most in critical applications?
Yes, so non-destructive testing is really picking up. And now, if you see with that, now robots and cobots, even
Mhm.
drones are the new technology, which is really good for us to use, which gives repeatability. What we can say that reliability of the results,
Mhm.
accuracy, and uh, you can say the same approach which normally having an issue with human intervention. So it's really good to have non-destructive testings related checks as a quality checks in the process. Normally, there are many NDT techniques which is popular based on
Mhm.
ultrasonic testings, or you can say phase array, acoustic emergence testings. These are the very common testing which is advanced in its type. So those
Mhm.
testings are really good to go for any testing is to be monitored. Normally,
Mhm.
when you have a critical applications, reliability comes from method selections aligns
Mhm.
with damage mechanisms. So normally when you want to see NDT, so NDT there are normally used for fitness for purpose for any equipment or
Mhm.
piping to have its integrity to verify. So there are many standards. If you say ASME, Section 5 is normally giving you information about NDT techniques. Also, you can say ISO 9712, which is normally used for personal qualifications for non-destructive testing personals. Also, API 579-1 or ASME FFS1, that is
Mhm.
fitness for services, are the normal standard which give you the informations related to non-destructive testing, which we can
Mhm.
use for critical applications.
Mhm.
Uh, Only method is not going to survive. At the same time, we must have a qualified procedure,
Okay.
trained personnel, and proper data interpretations. Because when
Mhm.
we say the robots, cobbers, and drone, so they give you the live data and they capture into the system. So now
Mhm.
challenges is not to do NDET by your own, but you need a procedure by which you can adjust the NDE methods, how to apply and how to verify those surfaces with respect to weld, heat affected zone or base material requirement.
Okay.
Rather that initially, the people are doing with their own, with the hand. So
Mhm.
now that is replaced with all the AI models. So now the personal training is not the skill how to scan the surface. Rather, they need a skill that how to place this sophisticated equipments in place by which they will understand the correct interpretations of the results. So
Okay.
these are the challenges which is really good for us to have advanced non-destructive testing for critical applications. And normally, if you see with respect to height, so there are scaffolding applications, and then traditionally doing non-destructive testing is a challenge. So when we say that high confidence techniques which required, that is, you mean to say good technology in terms of non-destructive testing, then you can use phase array UT, that is for weld and crack sizings to verify. You can go for corrosion mapping UT for remaining life assessment for any equipment and piping. Also, you can use acoustic emissions for active crack detections. Then additionally, you can say guide waves UT, that is for long range pipeline scanning. So these are the methods you can use as an NDT, but I will say that NDT does not prevent failure. It is only used for detections based on NDE, which we do for any equipment and piping.
Okay, sir. So, sir, what are some real world examples where early material failure was avoided thanks to smart engineering or inspection protocols?
Yeah, this is also in line with what we discussed before. Like some of the best, you can say, safety stories never makes headlines. Normally, these are going with very quiet approach. So when we say that a crack detected earlier, uh, or you can say corrosion found under insulations, or there is a metal upgrade before commissioning. So these are the things which is normally not known to any one of us. So those are quiet, and normally these things are uh, going in a very phased manner. So those never come up on the surface. So in almost every case, someone choose to go beyond minimum code compliance. So this is really good because code is giving us the minimum requirement. We can
Okay.
definitely go beyond that, and
Okay.
that's decision prevents prevail the shutdown or an accident, which normally we think of for any safety hazards in the industries. So this is really good examples where we can go for corrosion under insulations applications. So nowadays, um, there are certain corrosion monitoring sensors are there. So not only the coating and insulations play the role, but also sensors which give you the informations about live uh, water phase, or you can say corrosive products normally observed over the surface of any pipe or vessels can be predicted earlier. And
Okay.
this is how we can understand based on the revised standard API 580, API 581 is normally giving us information about risk-based inspections philosophy. So this standards is focused on whether failure is most likely or most severely going to be there or not. So in each
Okay.
case, engineering judgment uh, exceeds minimum compliance, and that made the differences to us. So my normal way of understanding about the real world experience or examples which we want to go for with the help of smart engineering is to go with more monitoring tools, which is listed in API 580, 581, and that can control beyond what our normal inspections methodology to understand damage mechanisms in terms of cracking and thinning.
Okay. So, sir, like during our conversation, you have shared with us a lot of international standards, a lot of international codes. So, how do you manage compliance without compromising safety or performance?
That is good questions. Notice that I use sometimes ASME, sometimes ISO, sometimes API, sometimes I'm saying NIST. So that is really means is a lot of mix in terms of standards because some are origin from US, some are origin from Europe.
Yes, sir.
Standards which we have to cross refer even uh,
Mm-hmm.
to understand any equipment or piping to be fabricated or to be inspected. So
Yes, sir.
it's really interesting for us to know that there are many standards available worldwide for one applications. For example, say pressure vessel constructions. So
Mm-hmm.
this standards you have to work together. You cannot use
Mm-hmm.
isolately any one standard because
Mm-hmm.
there are many requirements which is stringent with respect to
Mm-hmm.
ASME, to ISO, to API, or to NACE. So
Mm-hmm.
my understanding for this particular international standard and code using, that is
Mm-hmm.
essentially because it gives requirement for any
Mm-hmm.
uh, equipment or fabrications to understand their constructions.
Mm-hmm.
So when we go for minimum requirement, which is a contractually as per code and standard, which we have to abide in any case. But
Yes.
if we want to go for only minimum requirement, then it is not compromising sometimes safety to the large extent. So
Mm-hmm.
my takeaway for reading the standard is we have to go beyond the limit which is specified in the standard, so that
Mm-hmm.
we can give more uh, stringent conditions which gives safety and reliability of equipment and piping.
Okay.
So just to say one word, one sentence, like strong safety cultures treats codes as a floor, not
Mm-hmm.
guidelines.
Okay. Okay. So, sir, finally, looking forward into the future, what advancements in materials or safety technology are you most optimistic about in protecting critical energy infrastructure?
Okay, so this is normally when we understand, then this can be particularly optimistic about hydrogen resistance alloy and coating. So that is one part which is normally used for next generation's energy systems utilizations, because hydrogen is a new fuel which we have to use in almost all our vehicles. So this is
Mm-hmm.
one area. Second is advance in sensing technology. So normally technology which is embedded directly into material gives its life. So that is one another point which is important for us to add. AI assisted inspections interpretations. So normally we go for any data. So now data is the next generation's boom. Like if you have more data, you are really good for interpreting the right damages or applications related to NDE. So that also gives reduce human basis and outside into the errors part of any things. Also, lastly, greater insight into material selections. So nowadays there are new materials are raised and technology is revolving, and the design life and other tools which is in the place, which normally good for asset integrity framework,
Mm-hmm.
go beyond the normal standards. So when we say that standards like ASME 31.12, or you can say section 9 for ND, in this case we have to approach in a way that the future of safety isn't thicker steel. Uh, when we say that do safety, then we say that instead of 10 go for 20 thickness. No, that is not the requirement, because it
Mm-hmm.
increases the cost, and nowadays cost, time, and quality here because of the. So that's why we are not for thicker sections inspections in place. Rather,
Mm-hmm.
we have to use smart materials, embedded sensors, and data-driven decisions. Can be better for us to reduce the risk to students. And that is why the new generations or new engineering uh, in terms of NDE or any other inspections, digitization. So this is how we
Okay.
have to think of
Mm-hmm.
for next inspections and testing requirements.
Sure, sir. So, finally, I would say this was a very powerful and deep dive into the world of safety engineering, material science, and infrastructure reliability. Thank you, Mr. Urvesh, sir, for sharing the principles, practices, and insights that help keep some of the world's most critical energy systems safe and secure. To
Thank
everyone
you.
out there listening, yes, sir. So, to all our audience, if you found this conversation valuable, follow the Hack Lab podcast and share it with engineers, safety leaders, and decision makers in your network. Let's keep safety at the center of innovation. Thanks for listening. Until next time, take care and have a nice day. Bye bye.